Hello, dear friends. My name is Konstantin Trushin. I'm a senior software engineer in Percona. And today we will be discussing Percona server for MongoDB with focus on data at rest encryption and key management for the latter. So in today's talk, we will cover what Percona server for MongoDB is and which encryption types it supports. We will also see how to set up data at rest encryption and change keys for it. We will take a closer look at some aspects of working with key management systems and draw some conclusions. And finally, I will be glad to answer your questions. Technically speaking, Percona server for MongoDB is a fork of MongoDB Community Edition and maintains backward compatibility with the latter. On top of its upstream, it implements some additional features, for instance, various authentication mechanisms and backupping and so on. And many of those features are especially useful in enterprise environments. But today we will focus on securing user data with data at rest encryption. One can set up three types of encryption in Percona server for MongoDB. The first one is in-transit encryption, which is basically a fancy name for ubiquitous TLS connections between client and database nodes, as well as between nodes in a cluster. The second type is in-use encryption, which means encrypting data in database server's memory and decrypting it on the client side before use. And the final type is at-rest encryption, the topic of today's discussion. That means that database server encrypts all the data before writing it to the disk, so that if someone gets unauthorized access to the storage media, they still can't read the user data. You might be wondering why we need data at rest encryption if we can simply set up an encrypted file system on our disk. And it turns out that data at rest encryption has a number of advantages. First, it encrypts only necessary data against all the data going to disk, which can potentially improve performance. Second, data at rest encryption eliminates the risk of accidental revealing of plain data by copying database files to unencrypted storage media, for instance, during backup. Finally, organizing secure and convenient storage for encryption keys in disk encryption can be challenging. In contrast, Percona server for MongoDB supports two types of key management systems, also known as KMS, and you can choose either of them. Let's look at how data encryption works. First, I'd like to remind you that Percona server for MongoDB keeps user data in the form of documents organized into collections, which in turn are organized into databases. When a Percona server for MongoDB creates a new database, it also generates a cryptographically random symmetric key for that database. On disk, a database is mapped to a number of files, one per each collection or index. Percona server for MongoDB encrypts all the data it writes to those files using AES, working in one of two chaining modes, with the key generated for that database by the server. The key itself goes to the encryption key database, which is then saved to disk and encrypted with master encryption key. This two-level approach will enable efficient master key rotation, as we will see a bit later. Setting up data at rest encryption requires a clean data directory, because Percona server for MongoDB can't encrypt already existing files. The perfect time to do so is when you initialize your deployment, and clearly it has no data yet. As a result of setting up data at rest encryption, we get a master encryption key, which we must store in some external system. When later Percona server for MongoDB restarts, for whatever reason, it usually already have written some data to disk, and now it needs to decrypt it. For that, it takes master encryption key, decrypts encryption key database with that, and then uses per database keys for decrypting the actual user data. On the right, we can see an example of configuration file for Percona server for MongoDB when we enable data at rest encryption. We must set the enable encryption parameter and also set up one of 3 options for storing master encryption key. The simplest one is keeping the key on a local file, but needless to say that it is not a secure approach and should never be used in production. And we won't discuss it further, and we'll concentrate on 2 other options, KMIP and Vault. One of the 2 key management system types that Percona server for MongoDB integrates with is systems that implement key management interoperability protocol, or shortly KMIP. KMIP defines objects it can manage, operations on those objects, and transfer encoding between a client and a server. In terms of KMIP, our master encryption key is just an object of the symmetric key type, and that we can store on a KMIP server with some unique ID, which is typically chosen by the server. An example of that we see in the picture on the right. KMIP associates the state attribute for each managed object. Later we will see how that attribute serves as a foundation for an important feature in Percona server for MongoDB. And Percona server for MongoDB has an embedded KMIP client for communicating with any server that implements the protocol. As an alternative to KMIP, one can use Vault for storing master encryption keys. Unlike KMIP, Vault is not a protocol with multiple available implementations. It is a particular software which implements its own unique protocol, all of which are developed by HashiCorp. Vault implements its capabilities via so-called engines. And we are interested in a version key-value secrets engine, which essentially stores sets of key-value pairs. Percona server for MongoDB constructs a single entry secret where a master encryption key is encoded in base 64 and serves as a value for an implementation defined key. Before we can use an engine, we must initialize it at a particular path on Vault. Within an engine, a secret is located by its relative path and version. We can define the absolute secret path as a concatenation of the engine's mount point, the fixed data token, and the relative path. And we can think of a tuple of absolute path and version as more or less identifier of a secret on Vault. In the picture, we can see an engine mounted at MongoKey's prod path with 3 versioned secrets, where their relative paths are derived from Mongo node names. And each secret has a different number of versions. By default, Vault keeps only 10 versions for each secret. And later we will see what that limitation means and how Percona server for MongoDB deals with its implications. Now, after we have overviewed 2 key management systems, we can see how to configure Percona server for MongoDB for working with each of them. And we start with KMIP. So on the right, we see the excerpt from a configuration and for setting up Percona server for MongoDB to work with the KMIP server. We basically specify the server endpoint and parameters for mutual authentication. In the sequence diagram on the left, we see two blocks. The first one shows what Percona server for MongoDB does when a clean instance is initialized. First, it generates cryptographically secure symmetric key and then registers it on the KMIP server. In response, it gets an ID which it saves to a disk. During subsequent restart, our configured node already has some data and needs to decrypt it. And now the process is reversed, as we can see in the block 2. Percona server for MongoDB reads key ID from the disk and requests a KMIP server for the key with that ID for decrypting encryption key database. Configuring Percona server for MongoDB to work with Vault is not difficult either. Basically, we specify the server's endpoint in the same way, and specifying authentication options is slightly different. But the most significant difference is that key identifier on Vault is compound and consists of two parts, as we saw a bit earlier. So one part of that identifier should be specified in the configuration. It is absolute path of the key. And it doesn't even require for that key to even exist on Vault. So it's our planned path, so to speak. Similar to KMIP, block 1 is in the sequence diagram on the left. Shows what Percona server for MongoDB does at initial clean start. It also generates a key, puts it on the Vault server at the specified path, and gets the version in return, and saves both path and the version to the disk. And again, during the restart, it reads path and version from disk and requests the Vault server for the key. And that is what is required to set up data at rest encryption with either of two key management systems. But as a main action of data operation is replacing that master encryption key on a regular basis. It's similar to that we replace passwords on our personal laptops, and should be done for basically the same reason. And here, with the example of KMIP, we see how to do that. We stop the service of Percona server for MongoDB, add one entry to the configuration file, and start the service again. In this mode, Percona server for MongoDB doesn't serve any client queries. Instead, it replaces the keys. And when it is done, it just exits with log messages and successful exit code. Now we need only to unset that configuration parameter and start the service as usual, and we are done. Internally, during master key rotation, Percona server for MongoDB reads ID of the old key from the disk, requests the server KMIP in this example for that key, and decrypts encryption key database with that key. Next, it generates a new key, registers it on the server, and after getting the ID from the server, it encrypts master encryption key database with that new key. And the ID of that new key goes to the disk. Usually, master master key rotation doesn't take much time because we saw that it needs only to re-encrypt the encryption key database rather than all the data set. In this diagram, we saw master key rotation with the example of KMIP server. For Vault, it is done precisely in the same way. We add the same parameter to the configuration and do the same set of actions. Even the sequence diagram is similar. As you have probably already mentioned, it resembles our previous one, but with blocks 1 and 2 reordered. And for the Vault, it is also the case. That master key rotation is a planned replacement of encryption key for data at rest encryption. But sometimes we need to do unplanned replacement because, for instance, we learned that the key was compromised. And to do so, we must identify which node uses our compromised key. That problem is not difficult to solve for Vault, because if relative secret paths are derived from node names, we obviously get the node identifier in the, on the Vault server. But for KMIP, the story is a bit more complex, because KMIP server generates ID for any managed object itself, and that ID doesn't have any valuable information, doesn't have any connection with the node where the key came from. But that doesn't make node identification impossible. And here, our state attribute from KMIP comes into play. That diagram is basically taken from the KMIP standard and shows all possible values for state attribute in the boxes and actions which must be taken on the managed object to transition it from one state to the other. For instance, any just created or registered object is in preactive state. Then it is desirable to activate our object as soon as it becomes used for any activity, like encrypting our data. Next, when, for instance, we learn that our encryption key is compromised, a security engineer just conducts the revoke operation on it with compromised reason, and that way transitions it to the respective state. Now we are ready to see how Percona server for MongoDB utilizes the state attribute in order to track that the key is safe and sound. We saw earlier that register operation on our sequence diagram was written in like bold font. Basically, it means that it is a compound thing, and essentially consists of two steps: actual registering and following activation. So after Percona server for MongoDB encrypts anything with generated key, the key itself is in active state. Next, when Percona server for MongoDB restarts, it requests the state from the server before actually requesting the key itself. And Percona server for MongoDB verifies that our encryption key is in active state and hasn't been transitioned or deactivated or compromised or something like that. If that is not the case, Percona server for MongoDB refuses to start and writes detailed error message to the log. But checking a key state is not limited to a starting phase. A running node of Percona server for MongoDB, in parallel with serving user queries, periodically requests the state attribute for the key from the server and checks that this state is still active. That is called key state polling and happens every 15 minutes by default. So in case of security accident, a security engineer just needs to revoke the key on the KMIP server, and his job basically ends here. Percona server for MongoDB will soon notice there, and as soon as it determines that the key is in any state except active, it terminates with like extensive log. That may seem scary, like terminating the running service, but it is not so scary as it can seem, because first, usually we have a number of nodes, like a replica set for serving user queries, and if one node terminates, it's not the end of the time. Next, this terminating is basically a signal for operations team that something went wrong. And since the terminating follows extensive logging, and Percona server for MongoDB exits with a very specific exit code, operations team can quickly notice that and conduct master key rotation to eliminate that compromised key from the system. And after that, all nodes will run with secure keys. That mechanism has basically two advantages. First, it provides separations of concerns between security team and operations team. Security team doesn't need to know anything about where the key is used, what that all the databases are, and so on and so on. Similarly, operations team doesn't need to do something extraordinary to keep the databases in secure state. It only needs to have ordinary monitoring, and as soon as monitoring notices that a node terminated, master key rotation can be run. It can be even automated, so everything happens without manual intervention. And in that way, operations team doesn't need to manually examine all and each node in their probably very big installation to find that particular one whose key got compromised. Now, I'd like to discuss the approach Vault takes to keep secret versions. And we should be aware of it because it allows to better understand the behavior of Percona server for MongoDB and the log messages it may produce. Each time we create or rotate master encryption key, we add a new version to a particular secret. Vault, however, limits the number of versions it keeps for a secret. And when the limit is reached, each new version silently and irrevocably overwrites the oldest version, which we particularly have for that secret. And we can model that process as adding an element to a circular buffer of predefined size. The Buffer size and maximum number of versions are governed by the max version parameter, and the danger comes from the fact that this parameter is only 10 by default. That means that adding 11th version will remove the first one. And if the key stored in that oldest version is still in use in a particular node, that means that data loss, because we can't decrypt the data anymore. We can alleviate that problem by increasing the max versions parameter on the vault server, either for a particular secret or a whole secrets engine, or both. In the latter case, Vault chooses the bigger of two maximums. Vault supports values as high as 24,000, if I remember correctly, for the max versions. But even if we set up that high value for the size of our circular buffer, Percona server for MongoDB needs to check whether there is a free space in that buffer before putting a new encryption key on the Vault server. And it does so as a part of a compound put operation. So when the check max versions configuration parameter is enabled, which is true by default, Percona server for MongoDB requests secrets engine configuration and the secrets metadata from the Vault server. The latter keeps max versions and the current most recent version, so that information is enough to determine if there is an empty space in our imaginary circular buffer. If it is so, Percona server for MongoDB puts a key to the Vault server in compare and set mode. That means that it asks the Vault server to check if the current most recent version is still as we get from the secret metadata. That ensures that our conclusion about free space availability is still relevant. And for the described mechanism to work, Percona server for MongoDB needs additional read permissions on the Vault server. Unless those permissions are provided, Percona server for MongoDB will refuse to put any keys on the server and will produce extensive complaints in the log about that. And to give that permissions, we can throw in a very basic set of configuration on the Vault server. So we see 3 blocks of something in the example. The first block enables manipulating with all the secrets on a particular secrets engine. And the following 2 blocks provide access to the metadata of secrets and the configuration on the whole secrets engine itself. And also, we see the example comments how we can increase max versions for the particular key in the whole secrets engine. Now, I'd like to discuss availability and licensing aspects of both KMIP and Vault. KMIP, being just a standard, has multiple commercial implementations. On the open source side, we have a PyKMIP project, which is licensed under Apache 2.0, but it seems it is kind of more research project, which is suitable only for testing, and on top of that, it doesn't seem to be maintained recently. A more recent development is KMIP Go project from OVH, which is also licensed under Apache 2.0. As far as Vault is concerned, for a long time it's been in its own league, because it's not a standard, it's a particular software from HashiCorp, which works by its own rules. Vault comes in two editions. Community edition, which is not even a true open source, but its license still allows you to run it in production unless you compete with HashiCorp itself. And Enterprise Edition, which obviously has commercial license, but interestingly, it implements KMIP. So if you are okay with the licensing and cost, you can have both worlds in one piece of software. Finally, there is OpenBAO project, which is backed by Linux Foundation and re-implements Vault Community Edition and true open source license. In summary, we recommend enabling and considering setting up dated REST encryption at the planning stage of your deployment. Though it is still possible to encrypt an already running replica set, that would be quite a tedious process. Nobody wants to execute on their production data. We should not forget about periodically rotating master encryption keys, at least once per year, and be prepared for security incidents and automate our rotation in case of some key gets compromised. Also, we should not forget to tune Vault configuration if we choose to use that software for the seamless experience with Percona Server for MongoDB. And finally, if you need any assistance in running your databases in general or data at rest in encryption in particular, don't hesitate to contact Percona. And as the last slide, here we have some resources you may be interested in. The KMIP standard, implementation from OVH, documentation of both HashiCorp's Vault and OpenBAO, Percona blog with many interesting topics, and two posts in particular which relate to today's presentation, and also documentation and forum for Percona Server for MongoDB. That's it. That's all I wanted to talk about today. Thank you for your attention.